Well, the current military engines, they have their full focus on best performance and thrust to weight. Currently, we are really running at the physical limits of those engines. That means we have aerodynamics that's always at the close to separation. We have thermodynamic cycles that run close both to the thermodynamic possibilities and to material capability. You can't go any higher with current available materials. Also, fatigue life is a concern. Some of the materials simply don't have sufficient life if we go to still higher temperatures. And of course, you have this concern of life cycle cost. So you want to extend component life, and you want to have maintainability with low number of personnel. Okay, fuel burn and emissions haven't been the highest priority in past development of military engines. Just from the cost side, there are numbers for the for all US flight operations. I think it's including Air Force and Navy. It's only 3% of the direct operating cost, but that's still $6 billion per year. That's the fuel burn of military engines. And now, with the target of having something like what is called global force projection, you want to have an aircraft or an uninhabited aircraft that can go everywhere in the world, and if there is no pilot in this aircraft, then all the restrictions posed by the human pilot can be removed. Your electronic has to survive, but not the pilot. And what will happen? You have this high-tech asset, but typically you will use it only a small time of the year. So the total life of the thing will go up to 40 or 50 years. And that means technology cannot be inserted at an easy path. Yeah? So you have to find a technology that's upgradable somehow. There might be midlife updates in such an engine. It might be that you cannot use the latest and best technology just now, but you might consider to insert it in 10 or 20 years from now. Noise is the same with the military didn't put a lot of concerns on noise. They now have some concerns in aircraft carrier operation just to the health issues of the personnel working there. And, but the newest fighter still have the same noise level as the ones that had been built 30 years ago. And of course the observability issues, IR, radar, acoustic, had been a main driving factor in the design of the current generation of aircraft and engine. And perhaps it will continue to be there. As said, if we have usage times of 40 or even 50 years, we have to find a way to handle obsolescence. In electronics, it's quite a big concern. Of course, in a new engine, during the first years, the only thing that counts is acquisition cost. And some technologies simply might not make its way into an aircraft or into an engine because nobody wants to pay for it, or the taxpayer will not pay for it. Okay, big areas where new technologies go in are materials, and electronics is another field. And we still now have research programs where we looking what we can do to existing engines to improve their performance and to make them usable for another 10 or 15 or 20 years. I had an example where now you can redesign compressor blades that had been designed in the 1970s, and with modern fluid dynamics you can make them more efficient, produce higher pressure ratios, and even give them more life. New materials had been the main driver of technology in the aircraft engine business. All the new engines wouldn't exist and wouldn't be so efficient as they are now if we wouldn't have all those new materials. High temperature materials were the key enablers for today's engines, and there is some potential to do better, but in metallic materials, if we go for composites, in the cold part of the engines, we may have carbon fibers similar now we have in fuselages or have in wings. There will be new metallic materials like titanium aluminide blades. Ceramic materials have been around, the idea has been around for decades, but they still didn't make it into a production engine. And we think that metal matrix composites might be one of the new enablers to have lighter weight, to have smaller engines, but there's a lot of technology research still being needed. And currently, one of the main problems is it's very, very difficult to predict life of a composite material. Oops. Well, this illustrates this role of materials. Here is the temperature in degrees Celsius, and here is the strength to weight ratio. And as you see, that is classical steels that are titanium alloys. That's basically the materials that are used in the front stages of the compressor. Here we have the nickel-based super alloys, which are all the high temperature discs and are the turbine blades. This is the new field of titanium aluminides, which is something that will have limited use in the rear stages of the LP turbine. And here we have this field of metal matrix composites, where there is some laboratory work and some demonstrators, but it's not yet in any existing engine. And we have this polymer matrix composites, which will be something that could be used in the front stages, in the fan. And here you have the special things like thermal barrier coatings or oxidation protection coatings, which can be made in thin layers but not as a bulk material. Okay, I think that's just something I highly recommend you to have some look at the European technology programs. There is a lot of material on websites. I can give you the links. I think they are also included somewhere in the material. There we have to really try to do something that's innovative, that's going beyond what is currently in the market. Things like the flow control core, which is having active elements in the compressor, having something that's passive by giving treating the casings, using new abradables, active core, that will something Wolfgang will talk about, I think. Yeah. And of course, if we want to go beyond the performance we can reach with current engine, we have to do something on the thermodynamic cycle. That means the flow of heat in the engine, in the process, has to be changed, and heat exchangers might be used. Will be very complicated flow passages, and a lot of new concerns, both from structural, from aerodynamics view. And eventually you could think about getting some heat back from the exhaust. That will be an engine that has a heat exchanger in the exhaust, which would give you a big performance benefit, but of course it will be a lot of additional weight, and it will be a complex geometry, and I'm looking forward to it, but may take some time. That just gives the idea what we can reach with new engine cycles. The conventional engine cycles is just as Sanjay mentioned, we have two compressors, we have two shafts that are connected here. We add the energy here in the combustion chamber, and we drive the two turbines, and they have an exhaust in the rear. Problem basically is a lot of heat you put in here is lost at the exhaust. Yeah? You produce a lot of thermal energy that just heats the surrounding air. And if you want, and that's the reason, because we can't get up with the temperature here, we're running into some saturation now. We have here the conventional engines. If you go up with bypass ratios, if you go up with core pressure ratios, then, and I think Wolfgang will talk about that, you increase the ratio of gaps, the losses, the aerodynamic losses, and the stability will simply put limits here. So if you go to a pressure ratio of 60, perhaps your losses will eat up all your benefit. Or if you go up to still higher turbine inlet temperatures, the cooling needed for the material will eat up all the benefit of the new thermodynamic cycle. And so if you want to lower the temperature here in the combustor, then you need to bring down the temperature level, and that could be done by cooling in the compressor. Between the LP compressor and the HP compressor, if you cool this air, then you can go down with temperature in a turbine, and then your blades will survive at a higher pressure but at lower temperature. And the total game changer would be something where you have heat exchangers that go put your heat in from the exhaust. Yeah? That would be a total new concept, but as said, that it's a complicated architecture, and I'm wondering if I will see it in the next 10 years or so. Well, these are a few of the concepts that are being considered now. It's in the European research program. Something like an active core, where we try to influence the flow in the compressor, stabilize the flow in the compressor, avoid losses by reducing the gap. You also can go to still higher compression ratios by some other flow stabilization techniques, and the radically new ones would be some intercooling between the LP compressor and the HP compressor, or the most radical concept would really to be combine everything, have intercooling here, and have feedback of the exhaust temperature to the compressor flow. Yeah.